Morning, everybody. Oops, I'm muted. Of course I am. Oh, for heaven's sake. Morning, everybody.
Morning.
Morning. Everybody have a good weekend?
Yeah.
Yeah? Good. All right, so any questions before I talk a little bit about the exam? All right, well, I'll just mention some things about the exam then. All right, so like I've mentioned in a couple of emails, the take-home portion, this is going to be open at noon tomorrow, which I believe is the 14th. And it's due at 2 p.m. on Wednesday. And again, I didn't write it to take a long time to do. I just want to make sure that you have a window of time to be able to do it. And this one, again, notes are okay. Of course, your calculator is okay. But don't look up for help on the internet. And no people. Yeah. And then the in-class portion is what we're going to do through the Zoom and the video. So the in-class portion, I'll have it open at, I think I have it set for 9:45. Oops. And it closes at 11. This one's no notes, no computer, no phone, all that good stuff. Now, of course, you'll have to pick up your phone to take the pictures to upload your work. I get that part. But other than that, there shouldn't be any phone touching. All right. This one will log into Zoom and show your video. Just so, again, from that proctored standpoint. Again, the main reason for this part is because this is going to be the stuff that's over the 7.3 and the 7.4 is the only part that's on your in-class portion. And the reason for that is I know that there are phone apps and websites that will solve all those problems for you really nicely without you have to doing anything. So that's why I'm doing it the way I'm doing it. Your take-home portion is 8.1a only, so there won't be anything with 7.1 3 or 4 in that particular one. So that was your law of sines and your law of cosine stuff. That would have been what was like on your homework that was due yesterday. And then the in-class portion is the stuff that we did before. So this is also the 7.3 and 7.4. This is also what the review for exam 3 covers. So you've got some extra practice problems on those on Moodle, and I'm gonna run through examples today of the types of problems that you could see in this part, and then the 8.1a stuff is you've got all those extra problems that I have posted on Moodle already. There's an extra law of sines and cosines handout. There is an application of law of sines and cosines handout with solutions on there. And then I believe I have a couple of videos as well on YouTube with law of sines and cosines examples. So I didn't post an extra review for that because there were already many different examples already for you on Moodle for that. So The only thing I did the extra review for was the 7.3 and 7.4, so you had some extra problems to look at for that for the exam.
What time will the Zoom be open on the in-class portion?
I will open it at 9:45. So I will be on there at 9:45, so I'll have it open then. Any other questions about the logistics stuff before I do some example problems of like what's going to be on the in-class portion?
To receive the questions for the in-class portion.
It'll also be on Moodle when it opens up. It'll be right on there as well. And if I can figure out how to share my screen and see the video at the same time, I'll do it that way too. I haven't been able to figure that out yet. I'm not sure I can do that, but I'll try. But it's definitely going to be on Moodle, so you can download it that way too.
Do we have from the full 9:45 to 11 to complete and upload it to Moodle?
Absolutely, yes, you do. Yep. As soon as it opens, you can start. Yep. Any other questions at all? All right. Well, let's do some example problems then, like that's in the 7.3 and 7.4. So remember your 7.3 was where we had the double angle and half angle formulas. So your sine double angle formula, of course, is your 2 sine x cosine x, and your cosine double angle formula, there were 3 forms of it. Your half angle formulas, there's a couple of those. The half angle formulas for the sine and the cosine look very similar to each other. Just have that one sign difference in the middle. And then remember also that you have to make a decision on the plus or the minus. Those depend on what quadrant you're in. So just to go through a couple of examples here where you might see what kind of problems you might see. Maybe you would be asked to find the exact value of, say, cosine of 7 pi over 8. So 7 pi over 8 isn't an angle that you know the exact value for cosine of off the top of your head. So probably going to be where I want you to use half angle formula. So we know, since I'm using the cosine, I'm going to want to use the 1 plus. And then we notice from the half angle formula that the inside of the cosine here is double the inside of the cosine here. So if I take 2 times the 7 pi over 8, I get 7 pi over 4. So now I got to figure out a couple of things. I need to figure out, do I use the plus or do I use the minus? And I need to figure out what cosine of 7 pi over 4 is. So remember, for the plus or the minus piece, I look at this angle. So using just the quadrants here, I know that all the way around all the way to here would be pi, which is 8 pi over 8. So I got to stop a little short. So this would be 7 pi over 8. So in particular, I'm in quadrant 2. And since we're in quadrant 2, the cosine will be negative. So I won't use the positive, I'll use the negative. And then I got to figure out cosine of 7 pi over 4. Well, again, if I think about my quadrants here, 8, if I go all the way around, that's 2 pi, which is 8 pi over 4. So 7 pi over 4 is short of 8 pi over 4. So I'm down in quadrant 4. All right, so for that part, I'm in quadrant 4, so it'll be positive, and it's a pi over 4 angle, so it's going to be 1 over square root of 2. And then leaving it like that is perfectly fine with me. So again, it's negative because the 7 pi over 8 was in quadrant 2. This one on the inside here, this part is positive. This part here is positive because 7 pi over 4 is over in quadrant 4. This we're just evaluating our cosine like we would any other time. Questions on one like that, at all, or what, on that one at all, or anything like that at all? All right. Another one you might be asked to do, and we've seen ones like this pretty much all semester. Let's say that you're given that the secant of theta is, how about negative 17 over 15, and let's say that it tells you that theta is in between pi and 3 pi over 2. Let's say you're asked to find, let's just do sine of 2 theta, let's do cosine of 2 theta, let's do tangent of 2 theta. And we might as well do sine of theta over 2 and cosine of theta over 2 while we're at it. All right, so just like we've done all of these problems this semester, it's best to start with a triangle. This one's not too hard to figure out where to draw your triangle because it specifically tells you where the theta has to be. It says the theta has to be between pi and 3 pi over 2. I just got an email from somebody. Can anybody else not hear me? Can anybody hear me? Yeah, you can hear me? Okay, I can see on my phone I had an email from somebody saying they can't hear me at all. So, let me email him back real quick. Sorry, I'm going to pause real quick so I can email him back and say that everybody else can hear me. So anyway, I wanted to respond to him real quick so that he didn't think I was ignoring him. Or, of course, half the time I feel like I'm talking to myself anyway, so I wouldn't have known the difference if somebody not emailed me. All right. Anyway, so I know that this is in quadrant 3. So I draw my triangle down in quadrant 3. And then I know that the secant is 1 over cosine, so I can label my hypotenuse and my adjacent. Hypotenuse will be 17. Adjacent will be negative 15. And then we can use our Pythagorean theorem, of course, to figure out the opposite side, which will be negative 8. So now I can read all of my trig functions for that particular triangle. So for the other ones now, we just need to use our identities. So for sine of 2 theta here, we can use 2 sine theta cosine theta. And we can read those right off the triangle. Sine of theta is negative 8 over 17, and cosine of theta is negative 15 over 17. And again, you do not need to simplify that for me at all. You can leave it just like that. Cosine, you've got 3 choices. Doesn't matter which one you use. I'll use the cosine squared theta minus sine squared theta. So cosine is 15 over 17, and sine was negative 8 over 17. So I just get the negative 15 over 17 squared, and then minus negative 8 over 17 squared. The tangent of 2 theta is 2 tangent theta over 1 minus tangent squared theta. And then tangent, of course, is opposite over adjacent. Your negatives will cancel, so I'll just write it as 8 over 15. So I have 2 times 8 over 15 over 1 minus 8 over 15 squared. So again, started off the problem just like we have all semester with drawing a triangle, and then just plugging in the pieces after using our identities to rewrite the double angles. We'll do the same idea for these using our identities. The only thing that we have to make sure of is whether we use the plus or the minus. So going back up here to our angle, I know that theta is between pi and 3 pi over 2. So if I divide everything by 2, I know that theta over 2 is between pi over 2 and 3 pi over 4. And the reason, again, I'm dividing everything by 2 is because I'm trying to figure out what quadrant theta over 2 is in. So I divide everything by 2. I get pi over 2 and 3 pi over 4 as my bounds for theta over 2, which means we're in quadrant 2. Since we're in quadrant 2, the sine is positive and the cosine is negative. Okay, so for the sine then, we'll get square root of 1 minus negative 15 over 17 over 2. And for the cosine, we'll get negative square root of 1 plus negative 15 over 17 over 2. And again, you could simplify this, but I don't expect you to. Any questions on that one at all? Okay. So those would be ones that would be like what I would expect you out of the section 7.3 stuff. Would be doing things like this. All right, then 7.4 was just solving equations. So for your solving equations things, we had things like, let's say you were asked to find all the solutions of, let's say we do, let's say we have 3 cosecant squared x equals 4. So when we do ones like this, it's probably easiest to isolate the cosecant first. So I'll divide both sides by 3. Take the square root of both sides. When we take the square root of both sides, we always get plus or minus. Square root of the top is 2, and the square root of the bottom is, of course, square root of 3. And ordinarily, it's a little easier for us to remember what the solutions are if we write it in terms of sines and cosines rather than secants and cosecants. So the secant is 1 over sine. So if I take the reciprocal of both sides, we're looking for where the sine of x is plus or minus root 3 over 2. So again, our strategy for this is to figure out where the solutions are from 0 to 2 pi, and then add multiples of 2 pi. So we know that we know the sine is equal to root 3 over 2 at pi over 3 and 2 pi over 3. That's where it's equal to the plus root 3 over 2. We know it's equal to the negative root 3 over 2 at 4 pi over 3 and 5 pi over 3. So this would give you the places where it's equal to root 3 over 2 or negative root 3 over 2 from 0 to 2 pi. And then to find all of the solutions, we add multiples of pi, 2 pi. So then this would be all your solutions. I just realized I wrote find to find all solutions. Sorry. I don't know why I wrote all this. Questions on that one at all?
Since this is going to be on the portion of the test that you said no calculator, is this, we're not going to have any of those ones that you basically have to use the inverse sign to get exact decimal?
Oh, calculator is okay. Computer is not okay. I don't want you playing around on websites. Your calculator is fine.
Okay, never mind.
Yeah. No, you're good. I didn't mean, if I said calculator, I didn't mean to. I meant computer. Yeah, calculator is perfectly fine. You will have ones that you'll need to do the inverse on your calculator. Yeah. Sorry for the confusion. I probably said the wrong word. Knowing me. Let's see if we do another one here. Let's say I ask you to find all solutions of, let's say we did sine x times secant x. Let's say we say plus sine of 2x equals 0. Well, it's probably a little harder than I want to do. I'll leave it for the time being. See what happens. This might not be a very good example. It might be harder than what I want, but it at least will illustrate part of what I want. All right. So the first thing that we notice is that we've got a 2x here, and the other ones have x in it. So the first thing we need to do is rewrite the sine of 2x as 2 sine x cosine x. Now notice that we have this already equal to 0, and we can factor out a sine out of both sides there, or both terms there. So I'm going to go ahead and factor out the sine. So now that we have it factored, we can set each piece equal to 0. Now this one, let's just do this one first. We have sine of x is equal to 0. We know that sine of x is equal to 0 when x is 0, when x is pi, 2 pi, 3 pi, or the negative. So I can just write that as n times pi. It's okay if you don't see this right away and you say x equals 0 and x equals pi, and then you put 2n pi for each of these. I'm okay with writing your solution that way. There's nothing wrong with that, because that still does the same principle we talked about of finding all your solutions in 0 to 2 pi and then adding multiples of 2 pi. This is just a little bit more shorthand way to write it. All right, let's play with this one. Let's see how ugly this particular one is. So I can rewrite secant x as 1 over cosine. And then I would need to get this cosine out of the denominator. So I'll multiply both sides by cosine x. So I get 1 plus 2 cosine squared x equals 0. If you solve this for cosine squared, this didn't turn out to be as bad as I thought it was going to. I would get negative 1 over 2 when I solve for cosine squared. Now, we're done, essentially, because the left-hand side here is the square of something, and it says it's equal to negative 1/2. So if I tried to take the square root of both sides, I'd be taking the square root of a negative number, which is undefined. So this has no solution.
What's the reasoning behind that?
When you take the square of a number, it's always positive. Remember that this is cosine of x squared, and it would be equal to negative 1/2. So if I tried to take the square root of both sides, I'd be taking the square root of a negative number. So it has no solution. Does that make sense?
So you can't do that.
Yeah, you can't do that one. If I wanted to make this have a solution, I could. If I would have started with this sign as a minus sign, I could have finished it off. But in this case, it's because if I square something and it's negative, then it didn't have a solution.
Okay.
The part that I wanted to illustrate, of course, with this one was rewriting the sine of 2x here as 2 sine x cosine x so that you could factor out the sine. That was the big thing that I wanted to do for that one. See if we can do another one that involves some factoring. Let's say I asked you to find all solutions of cosine 2x plus 3 cosine x equals 1. So much like the previous problem, we've got a 2x inside my cosine x here, but I've got a single x inside the cosine x here. So I need to use one of my identities to rewrite the cosine of 2x so that I only have a single x on the inside. Now, for cosine, we have 3 of them to choose from. So we want to choose what I'll call the correct one for this particular problem. There's not a correct one. They're all correct ones. But the one that makes the most sense for this problem is going to be the one that's in terms of cosine only, because that's what the other term is. So we're going to replace the cosine of 2x with 2 cosine squared x minus 1. So now that we get something that looks like a quadratic equation, so to solve that, we'll move everything to one side. So in particular, we'll subtract the 1 over to the left-hand side. And now this one should factor. So we get 2 cosine x minus 1 and cosine x plus 2 for our factors. And then just like before, set each piece equal to 0. And then isolate the cosine x in both cases. So the first one gives us cosine x equals a half. And the second one gives us cosine x equals -2. And now we approach this just like we approached the others. We look for all the solutions in 0 to 2 pi. And then add multiples of 2 pi. So cosine is equal to a half. It says it's positive. We're looking in quadrant 1 and quadrant 4. In quadrant 1, it's pi over 3. In quadrant 4, it's 5 pi over 3. And then again, we add multiples of pi. The other one, this asks when cosine is equal to -2. Well, we know that when we take the cosine of an angle, it's always between -1 and 1. -2 is not in between -1 and 1, so this has no solution. So this one gives us...
What are the bounds for both cosine and sine when you take the inverse?
Is when you take the what angles come out, or what you do the inverse cosine? Is that which one would you ask me? I'm sorry.
Yeah, like what's the bound, like you know if it's no solution or not.
Okay, so if I know if it's no solution, so this if you have sine of x is equal to something here, this has to be between -1 and 1. And then the same thing for cosine. Those have to be between -1 and 1 for that to work. And so the -2 is outside of that in this case. If you were ever in doubt, if you put it in your calculator, it'll tell you there's an error. Because if I go over here and do inverse cosine of 2, it'll say error domain, so that you know it's not in the right spot. Questions on this one? All right, let's do one where the angle is, or the inside is a multiple of x instead of just an x. So let's say you're asked to find all the solutions in the interval from 0 to 2 pi of, let's do, how about 2 cosine x plus 1, let's say do cosine of 3x plus 1 equals 0. All right, so we treat this just like we would do any of the other ones. We want to first isolate the cosine. So to isolate the cosine, we'll add the 1. Excuse me, try that again. We'll subtract the 1 and divide the 2. So we get cosine of 3x is equal to -1/2. And we don't worry about the 3 to start with. We do the same kind of thing that we were just doing. We just treat this like it's a variable, the 3x. We first look for when cosine is -1/2. So we're looking in quadrants 2 and 3. And we know that if it's equal to a half, it has to be one of the pi over 3 angles. So we must have 2 pi over 3 or 4 pi over 3. And if we were doing all of the solutions, just like before, we would add multiples of 2 pi. So notice that this process is exactly the same process that we've had so far, same ideas. Now we want to get x by itself. So to get x by itself, I need to divide everything by 3. So the first one, I'll get 2 pi over 9 plus 2n pi over 3. The second will have 4 pi over 9 plus 2n pi over 3. And now we want the ones that are in the interval from 0 to 2 pi. Okay, so in this particular case, and like I mentioned before, we know that this number in here basically gives us this many times the solutions as we would have had otherwise. What I mean by this is, notice that we had 2 solutions to start with in the interval from 0 to 2 pi. So instead of 2 solutions, we're going to get 6 solutions because of that 3. We're going to triple the number of solutions. All right, and the way we find those is we start by plugging in n equals 0. Then we'll plug in n equals 1. And then we'll plug in n equals 2. And like I mentioned before, we know if we start at 0, we always end at 1 less than what that coefficient was. So when n equals 0, we get x is 2 pi over 9 in this one. Over here you get 4 pi over 9. When we put in 1, you get 2 pi over 9 plus 2 pi over 3. If I multiply top and bottom here by 3, I get 6 pi over 9 plus another 2 gives me 8 pi over 9. In the second one, I get 10 pi over 9 because I get 6 pi over 9 plus 4 pi over 9. And essentially what we're going to end up doing, each time we put in a number 1 bigger, it adds a 6 pi over 9 in this case. So the next one's going to be 16 pi over 9 or 18 pi over 9. 16. Did I do that right? No, I added too much. It's 14 and 16, sorry. When I add, so we added another 2 pi over 3 to this one to get to that one. So we're adding 6 pi over 9, adding 6 pi over 9 to get to that one. So we end up with 6 solutions rather than 2. Questions on that one at all?
Is there like any like easy way to like, rather than like having to mental math that, to like see what each of those is plugged in, or you just kind of have to do them like math in your head?
I would probably just plug them in like what I was doing here. So you had the 2 pi over 9 and the 4 pi over 9. Maybe I would write them this way, perhaps. And then I know I'm going to add a 2 pi over 3 to the next one. And then I'm going to add a 4 pi over 3 to the next one. Honestly, if you get to this point and don't feel like simplifying the fractions, I'm okay with that too. This tells me you know how to find the solution. I don't really care. I don't really care about the arithmetic in general. So if you can get to the point where you can write this part down here and just leave it, and you know it's these 6 solutions, that's perfect with me. I don't want the trying to simplify the arithmetic to bog things down at all. This tells me you understand to put in 0 for n, 1 for n, 2 for n, which is perfect. The rest of it you can always put in a calculator. Does that help?
Yep.
Okay, cool. Any other questions on that one? All right. let's do one more here, and because I want to give you also one that what looks like what you would look like what would it look like in the calculator. So let's say you were asked to find all solutions to let's do cosecant squared x. Let's do minus cosecant x minus 12 equals 0. All right, so again, since we have a quadratic here, the first thing we're going to want to do is factor. So it looks like I got a minus 12 here, so I'm going to need a plus and a minus. I better use minus 4 and plus 3 to get the factor right. Oops, let's not find all solutions. I meant to say in 0 to 2 pi here. I don't care to put the 2n pi on the end. Not that it really matters. So we set each piece equal to 0. And isolate the cosecants. So we get to cosecant x equals negative 3, or cosecant x equals 4. This is, in this particular one, we're going to end up using our calculator, but even if we weren't, we probably want to convert this to sines anyway. So if we take the reciprocal of both sides, you get sine of x equals negative a third, or sine of x equals a fourth. Negative 1/3 and 1/4 are not values that we know the angles for to get the sines out of. So we'll do inverse sine of both sides. So we'll have inverse sine of negative a third for one of them, and inverse sine of a quarter for the other. All right, so let's go to our calculator. All right, so inverse sine of negative a third. Oops, I've got this in degrees. Let's change this to radians. Oops, what the heck just happened? That was weird. So we get about negative 0.3398. We'll write that down. 3398. And then the other one was inverse sine of a quarter. And we get 0.2527 for that one. All right, so those are the two solutions that we found by doing inverse sine. So notice that the problem asked us to find A, all of the solutions, and B, in 0 to 2 pi. So the first thing I notice is that this number, the negative 0.3398, isn't between 0 and 2 pi. Now we remember about inverse sine. It gives us angles in quadrant 1 or quadrant 4. So this angle down here going this way should be negative 0.3398. So if the first thing I'm going to do to make this be in 0 to 2 pi, I'm going to do 2 pi minus that. Basically add 2 pi to it, so that instead of going around to the negative direction, I'm going around to the positive direction this way. That gives me one of the solutions. The other one, Well, this was in quadrant 4. We also know that the sine is negative over in quadrant 3. So there's another solution over here. If all I'm worried about is the measure of this angle right here, the measure of that angle is 0.3398. I'm not worried about the plus or the minus. I'm just looking at how big that angle is. So if I start measuring from here and going all the way around, I have to do pi plus that little bit. So the other solution is pi plus 0.3398. So these are the two that you want. Okay, so again, we got the negative 0.3398 from the fact that we did the inverse sine. That's how we got the negative 0.3398. To get the solutions that we want for in between 0 and 2 pi, well, the first thing is all we did was just instead of measuring negatively, we measured positively. So we added 2 pi. That's how we got the first one. The second one was where we knew, okay, not only is the sine negative in quadrant 4, it's negative in quadrant 3. So I drew that angle in quadrant 3 that had that same measure, not worrying about the sine, just the measure, and then figuring out what it had to be if I started from the positive x-axis going around. So that was pi plus the 0.3398. All right, so the other one here, this one's good because we know inverse sine gives us an angle between 0 and in quadrant 1 or quadrant 4. Since that one's positive, that one's over in quadrant 4, or quadrant 1, I mean. So that one's good. We're good to go with this one. We just have to go find the other one. Okay, well, the sine is also positive in quadrant 2, over here. The measure of this angle, again, is 0.2527. Not worried about measuring from the positive x-axis or anything along those lines. Just how big is this angle? That angle has that size. Now, if I worry about measuring from the positive x-axis, well, all the way halfway around would be pi. I stopped short, so this will be pi minus 0.2527. So these would be your solutions to the second two. By the way, notice something here. To find the second solution for sine, I did pi minus the solution that I got. This is the exact same thing here for the second one. This is pi minus negative 0.3398. So when you're looking for the second solution for sine, you can always do pi minus what you got out of your calculator. The second one's always going to be pi minus what came out of the calculator. So the only thing that's really quote-unquote tricky is doing this 2 pi business here because it wants the angle between 0 and 2 pi. Questions on that at all? So again, going through all of these, this is the types of things that I would expect you to be able to do on the test. And doing these types of problems, notice that we went through them slowly, going through explanations of all of these, and we got done in 50 minutes. So if you're not worried about me going through explanations piece by piece by piece, you should see that the time shouldn't be an issue, and I'm giving you basically an hour and 15 minutes to do it as well. So I don't want the time to be the factor for finishing this up. Any other questions at all before I say goodbye? All right, well, if you've got questions about things, again, feel free to ask. The take-home portion, again, will open up at noon tomorrow, and you've got until 2 on Wednesday to turn that part in. And then otherwise, I will see you all on Wednesday. Have a good one, everybody.